To a lot of people, heck, maybe to most people, statistics is a little bit more like sadistics. And my job as Dr. C is perhaps to, if not change your mind, at least make it a little bit more easy. Classically, one might want to compare two populations, whether or not they did or did not like the new cheese-flavored treat, whether or not the medicine or the poison saved the rat. And of course, there are some problems. The distributions may not look similar, let alone symmetrical, and there's also problems about how it's administrated. You may have biases, both conscious and unconscious, on the part of the participants, both the observer and the observed, and as well as the willingness to participate both as a questioner and as somebody being questioned. And one way to deal with that is to do a double-blind study where nobody knows what really is going on. Further, there's a confounded aspect. You may falsely reject something that is true and accept something that is in fact false. Type 1 and type 2 error. So in traditional statistics, you try to make sure that the covariance approaches 0. It turns out in finance, we keep the covariance and throw out the variance. Let's start off by noting that the portion, the fraction, the weight that we would have in any portfolio is just the dollar amount in each divided by the total. And if you think about it, the fraction, the weights have to add to 1 or 100%. And the return to a portfolio is the weights times the respective returns, where the return, actually the net yield, is the terminal price minus the initial price of any security plus its income or dividend divided by its initial price. And the returns could be a decimal, could be a percentage. It's going to be the same regardless, just recalling how you do percents. And it's easy to show, in fact, so much so I'm not going to bother with it. That's exactly the same thing as you've took the total dollar amounts of each security and divided by the total amount of the portfolio. Now, what becomes interesting is the portfolio variance, the risk of the portfolio. Formally, it's the double sum, that's like a matrix, a square, of the weight of the column and the row of each security times its covariance, where we recall we have the covariance being the correlation times the two respective standard deviations. Here I'm using finance notation for a population in Greek form. We'll be talking about that later. If there are just two securities in a portfolio, you would have weight A and weight B. They add to 1. And the weight in A times the return in A plus the weight in B times the return in B would give you your portfolio return. The portfolio variance would be the weight A squared times its variance. We're going to show more about that later. Plus 2 times, that's because there's an A and a B and a B and an A. So it's the product of the weight A times the product of weight B times its covariance, plus the weight B squared times its variance, all added up. And if you want, we can substitute the fact that B's weight is 1 minus A's weight. Here's a graphical mnemonic of a general case and then a specific square case. So to give a bit of a contrast between the two, in sample statistics, you typically have a small number of populations, as well as often a small sample size, significance, the reciprocal of the square root of the sample size, and they use Latin, ABC notation. So while standard deviation is called S, and maybe the thing you're sampling is X, you do have one big notable difference, and that is because it's a sample, you want to adjust for that by dividing by the sample size n minus 1, whereas in the population, it's just n. In finance, we typically look at populations because
you really can't get any more stock data than you already have. You either have it or you don't. N tends to be very large with many securities. You use Greek notation because that's what they do, and therefore our standard deviation is now called sigma. And instead of, say, x, we might call it r for the return. We already talked about that. And the mean, instead of, say, x bar, would maybe be mu, which is Greek for mean. And recall now we divide by the number of cases. And of course, in both, the standard deviation is the square root of the variance. As we will see, we throw away the variance. In both cases, the covariance is calculated identically, although it sure looks different. You might say covariance, and then x minus the x bar for a or b or I or j times each other divided by the number of cases.
Identically in finance is the covariance, but here we use the notation using that sigma sign with a double subscript. It's confusing for the undergraduates, so we don't do it that way. But with a double subscript, because remember it's a row and a column, so that's the covariance. When I equals I or j equals j, then it's the variance. We'll see that again. And we can now call it r minus the mu for, say, I and j, or a and b, and again divided by the number of cases.
Continuing, things are the same. Again, the notation is just the only difference. Correlation is the covariance divided by the standard deviations. And the beta is, watch it, the covariance divided by one of the variances.
And that beta, or b, is the slope of a linear equation, which we will use to develop the capital asset pricing model, but not here. But we will show here why the variances disappear in any diversified portfolio. Looking at a general case for any number of securities, we have a weighted return. Again, weights add to 1. There's our double summation of a square matrix. And now let's separate where the i's and j's are the same or not. And if I and j are the same, well, it's times itself. That's the variance, the squaring, if you will, and all the others are not. And along those diagonals, that's the i's and j's are the same, it turns out those are the variances. And how many of them are in a square of n securities? There's n of them. So let's let the weight equal 1/n. So there's n variances, and because it's a square, there's n squared of them, and all those that aren't I equal j must be less that n, and there's covariances, and we again said that the weight is 1/n, and so let's see, how many do we get? We substitute n, and we find it's 1/n times the variances, and n minus 1/n times the covariances, and you let n get big. The first term, the covariance, the idiosyncratic risk, disappears, and only the covariance remains. So to summarize, in sample statistics, typically of fewer cases, it's not required, but they usually use Latin notation, and notable difference is the variance is divided by n minus 1 for the number of cases, and typically you try to be as confident that the covariance disappears, whereas in population statistics you often use Greek notation. You don't make that adjustment, you just divide by n for the variance, and you try to have the variance disappear. The covariance is computed likewise the same, but sure looks a bit different with drcinvests.